our next speaker is David Benisty. David is currently at Frankfurt Institute for Advanced Studies, and today he's going to talk about his work titled Weighing the Milky Way and Andromeda in an Expanding Lambda CDM Universe, Resolving the Local Mass Tension. David, please go on.
Yeah, thank you very much for the introduction. I'm now currently visiting in Frankfurt and also in Helsinki. And yeah, we'll start a new position in Leibniz over the summer, Leibniz Institute. And I'm going to speak about a subject which is more related to astronomy of the local universe, basically. But I mean, the impact of the cosmological constant or the impact of the cosmic expansion is also important to take into account in all of these scales. So I mean, in the past, I did like about how to constrain lambda from the local group and such stuff. I mean, this is not what I'm going to focus today, but actually what is the local group mass? And apparently, if you take lambda or if you take other expansion rates, you get a different prediction for the local group mass, and therefore this is important also for the local universe astronomy. So just like to give you an idea that also what we consider as the Hubble tension, this is also what you can call the lambda tension, the cosmological constant tension. So I mean, what appears in Einstein equation, this is the r minus 2 lambda. This is proportional to the Hubble constant square. I mean, it's also coupled to omega lambda. So it means that if you have this kind of like 5 tension in between the values of the Hubble constant, you also have a tension for this very fundamental cosmological constant. Okay, so I mean, this constant is affecting usually on very large scales, but also there is a non-negligible impact from Milky Way and Andromeda and other galaxy groups in the close-by universe. Now, to probe the impact of this kind of like repulsion force, we need to calculate what's called the geodesic equation. Okay, so I assume that you have a particle in expanding space-time. And then what you get something that looks like the Newtonian force. This is assuming low energy limit, because this is a valid assumption for the history of the galaxies. But also you get some repulsion force from the lambda. So I mean, this is a linear, yes, because you have to multiply this by r. Now, if I want to know on which scales this lambda is important for these galaxy groups, I can just like to do before, I go like to simulations calculation, just like to do state back on the envelope calculation. So I mean, if I'm taking the left-hand side, the force, that force in between the Newtonian attraction for certain bodies and the repulsion to 0, I'm getting what's called the zero acceleration surface. Okay, so this is kind of like some distance that related like to the mass that contained inside some sphere or inside like this system. And this is the distance where the cosmological constant is canceling the Newtonian force. Now, if you do the Virial Theorem, you can actually show that if the system is virialized, this is the maximal surface that kind of like surrounds the system and sets the boundary. Okay, so just to give you numbers. Okay, so I mean, Milky Way and Andromeda, this is kind of like from some AI generator. Obviously, we don't have a picture of Milky Way and Andromeda. This is the Milky Way. This is the Large Magellanic Cloud. They have a non-negligible impact that we have to take into account that I will discuss in a bit. And this is the Andromeda galaxy. And these are like the two most massive galaxies, Milky Way and Andromeda, and we have a lot of dwarf around them, a lot of dwarf galaxies. So the separation, the distance in between Milky Way and Andromeda is about 1 megaparsec, 0.77. And also we know with very high precision from recent measurements by De Marel et al., what is the radial velocity. So I mean, you see this is about 100 kilometers per second. So this is kind of like a galaxy that fall into us. Now, about the tangential velocity of Andromeda, we have different estimations. They are related to a different calibrations that or they are coming from Hubble Space Telescope or from Gaia, from the proper motion of different stars and such stuff. So I mean, you can get a different estimation. But I mean, the combined estimation, this is about like 60, but the errors are pretty big. Okay, so we have also a detailed knowledge about the tangential velocity. Now, what I told you about the cosmological constant, if you recall, I mean, this is the distance. If I have like a system where it's spherically symmetric or nearly spherically symmetric, I mean, Milky Way and Andromeda, it's nearly spherically symmetric. I have a paper about it, but I'm not going to discuss about it. Why? But here you can see that this is the distance where the cosmological constant should be dominate. Now, if I put inside the M, the total mass of Milky Way and Andromeda, so the mass of the Milky Way, as you will see, is about 10 to the power of 12 solar masses. And the mass of Andromeda, it's about almost 2, or around 2. So if you put in total 10 to the power of 12 solar masses, you get that the distance where the cosmological constant canceling the Newtonian force, this is about 1.5 megaparsec, which is 2 times the separation in between Milky Way and Andromeda. Okay, this is a very surprising results. Many astronomers are surprised by that, but I mean, this is correct. But it is possible to extend the acceleration surface. I mean, what is the distance where the Newtonian force is canceling the lambda force to a surface if you have two bodies. This is what I've done in this paper. But what you can see that if we have the Milky Way and Andromeda, this is the separation in between Milky Way and Andromeda, you can create kind of like a sphere around it. This is the turnaround surface, or a surface around it that looks like a bit egg, okay, like an egg, but it's very close to a sphere. And this sphere actually gives you the boundary for long time solution. So if you are integrating all of these dwarf galaxies for a long time, all of the points that you see here, these are the dwarf galaxies. But if you are taking the solution for a long time, or that the galaxy is supposed to infall inside the Milky Way and Andromeda, or that some of them will run away to infinity. Okay, this is kind of like the long-term solution for this system. And also Milky Way and Andromeda, also they are infalling to each other. So obviously what you can see that there is kind of like a surface that surrounds this galaxy, and also for other galaxy groups, that gives you the boundary or sets you the decoupled from the local attraction to the cosmic expansion. Okay, so why I'm giving you this introduction, obviously you can see that the Milky Way and Andromeda, they're really affected by the cosmological constant impact. Now, what I found recently also, that it's really gives you different masses estimate. This is what I'm going to show, which depending on which background you have. So it means that if you are only including the the repulsion force of the cosmological constant, just lambda, or you are including the full lambda CDM model, as you will see in a second, you will get a different mass estimate. So I mean, how can I actually speak if I have like two bodies? I mean, for instance, Milky Way and Andromeda in some background, how can I speak about the effect of the expansion? So I have to define my spacetime properly. So we all know what's called the Sitter-Schwarzschild spacetime. So this is just including the cosmological constant. And then you assume a spherically symmetric behavior. And then from the geodesic equation, you can get, as we saw, this repulsion force. However, if I'm assuming, this is what's called the Mc-Vitte spacetime, that I have two bodies, that they experience some potential, some force, but also that the background itself is expanding with some scale factor inside, then the lambda force that you saw is actually changed to A double dot over A. Okay, so A is the scale factor of the universe. Now, why this is so important? Because as you can see in this plot, this is the ratio in between A double dot over A and this lambda force. The lambda force is constant for the whole history. Okay, this is just like a repulsion force. However, this A double dot over A, when you have a matter-dominant universe, the space-time is attractive. This is what you can see here, that you have a negative force. But then during I mean, after like about redshift 2, right? I mean, this is kind of like the domination of the cosmological constant. When we have a domination of the cosmological constant, then this A double dot over A is become a repulsion force. So it means that for the equation of motion of Milky Way and Andromeda, if we try to estimate their motion, they are experiencing different forces for different times. Okay, so it's not just only the Newtonian force, but also the embeddings give you different history or different experienced force that these two galaxies they have. So how we can estimate the mass? There are a lot of methods. I'm going to show at the end like few different methods that are compatible with my estimate. But one from the classical estimate, it was invented by Kahn and Voltaire and also extended by Donald Liddell Bell in 1991. And then the model is very simple. you assume that you have two galaxies. I mean, you treat them as point particles. I know that we're speaking about two galaxies, but I mean, this is where we go to simulations, okay? How to explore the further dark matter halo and so on. But I mean, for the simple assumption, you just assume that you have Milky Way and Andromeda, and they started initially in a very small separation, okay? So what you can see in this plot, I tried, I mean, I'm going to show, I'm going to discuss this about like lambda or a double dot over in a second, but here you can see that I tried just like to backwards in time, to run the Milky Way and Andromeda backwards in time for different masses, and then to see what is going to be the separation at the Big Bang. So anytime that you approach some minima, this is the timing argument of prediction. So it means that this is supposed to be the correct mass or the corresponding masses, okay? So that actually fulfilling the timing argument, that in the Big Bang, they started from a smaller separation. Now, the first one, we found that lambda, the cosmological constant, is actually increasing the timing argument mass by 10, 13%. It was Partridge and Love and Hoffman in 2013. And it was a very surprising and important result. And what I found lately that actually this A double dot over A is decreasing the mass by 10%, okay? So it means that if we are taking a look on the full lambda CDM history, because we have in earlier times an attractive force, the timing argument mass could be lower. Now here you can see the dependence between the timing argument mass to other, like the edge of the universe or the Hubble constant. And obviously in all of these estimates, you see that A double dot over A is the lower one. Now, why this is so important? I mean, why I want, here you can see like the different values with the arrows inside. So I mean the A double dot over A lowering the mass. Now, why we actually want to relatively push the mass of the Milky Way and Andromeda to be lower? Because the mass in the literature, the mass of Milky Way and Andromeda, the timing argument mass, sorry, is a bit biased high. And there are different kind of like ways how to deal with it. Usually it's kind of like to probe by simulations what should be the correction. So here you can see in this nice paper by Sawala et al., they took different mass estimate for the Milky Way and different mass estimate for Andromeda independently. And then you see that like the mass of the Milky Way is about 1 10 to the power of 12 solar masses, and the mass of M31 is in between 1 to 2. I mean, by like the 1 confident bounds. And so in total, I would expect that the mass is going to be about 3, okay? But if I'm using just like the timing argument itself, I mean, this is what you see here, for instance, in this line, Lee and White. This is give you 5 and even higher, okay? So obviously we need to correct this timing argument in order to probe the correct mass. But as I told you before, also the embeddings, they take some effect at lowering the mass, but not that much, okay? So which other effects can we take into account? So there are 2 effects that I'm taking into account in order to probe the correct mass of the Milky Way and Andromeda. The first effect, that is my assumption that this is actually 2 bodies, but I mean, this is not necessarily correct because we have a void, right? I mean, we have a lot of dark matter. We have a dark flow around it. So, I mean, how can we probe this additional effect? So here you can see, for instance, some example by Lipskin et al., some example for n-body simulation. And then when you run this kind of like simulation for a long time, you can identify in your simulation different halos. And you call this kind of like halos, you call them galaxies, okay? Because you know from the simulation accurately what is the mass, what are the velocities, what are the distances. So when you are identify some pairs like Milky Way and Andromeda, they have a very similar separation, very similar velocities. You can say, okay, this is kind of like a 2-body that I can take from the simulation, and then to compare it with the analytical timing argument solution. So in the right plot, you can see these are the different total virialized mass, so the total virialized Milky Way and Andromeda mass from the simulation, versus the timing argument, the analytical expression that, or the numerical expression that I found for the Milky Way and Andromeda. Okay, so I mean, I took like the closest matches because they are inside the correct separation, inside the correct velocities, and so on and so on. And then you see that up to a certain factor, the timing argument is actually correct. I mean, they sit on this kind of like line of 1. But obviously, you have some bias that you have to take into account. Okay, so how you can calibrate by simulation? any pair that you are taking from the data, you try to find the pair also in the simulation, and then to find the correction factor. This is what I call like cosmic bias. So this is also can give you additional effect due to the fact that you are not actually probing two separate galaxies, but also two halos inside. Okay. And another effect, which is highly important in this system, this is the Large Magellanic Cloud. So I mean, the Large Magellanic Cloud, this is a very small dwarf a galaxy to the Milky Way, but also it changing the center of mass of the Milky Way, and this is why it's very important effect. So earlier paper by Eugene et al. I needed to put the reference, but okay, I'll put this like in later on. By Eugene et al., they try to find the corresponding Milky Way and Andromeda without the LMC. So what do I mean by this? It is possible to integrate backwards in time the Large Magellanic Cloud when it's like infall into the Milky Way and Andromeda, and then to integrate back, but without the LMC. So what you get from this kind of like double integration, for any Milky Way and Andromeda and LMC, you get a corresponding only Milky Way and Andromeda pair. So this gives you what should be the modified separation and the modified velocities due to the fact that now you're trying to ignore the LMC, okay? To integrate backwards in time the LMC and then forward in time without the LMC. So to see what are the corresponding R and VR and VT, but without the LMC presence. So what you can see here, these are like the different tangential velocity estimation. But then when we include the Large Magellanic Cloud, the integration of the Large Magellanic Cloud, we get a different distribution. So this is the distribution for Milky Way and Andromeda and the LMC. But then we integrated the LMC inside, we got a different separation and velocities. So I mean, this give us a different distribution due to the fact that the LMC changes the center of mass. Okay, so these are the two effects. I mean, so first we have the timing argument. We calibrate by simulations the halos around it. And also, due to the change of the LMC, we're getting also new separation and velocities, or because of the change of the center of mass. And as you can see here, and this is the main punch of the talk. So when I'm taking the timing argument plus lambda, the mass is higher. But if I'm taking the A double naught over A, as we saw in the history, the full history, so it's giving lower. But then when I'm including the simulation calibration, this is reduced to around 3. But then I'm including also the simulation and also the LMC. I'm getting a new mass estimate from the timing argument that usually the timing argument is biased high, to be around 2 10 to the power 12 solar masses. Okay. Now, why this result that now you can get from the timing argument a very low mass? It's very interesting because there are different estimations in the literature based on N-body simulation, based on the machine learning. They're giving higher mass, but also there are other estimates that are giving much lower mass, as the Hubble flow and the Virial Theorem. Okay. And this mass estimate is actually compatible with this other estimate. So I mean, the fact that we can get also such a low mass from the timing argument is a new result. So what do I mean by the Virial Theorem, or why do I mean by the Hubble flow? Just like to give you another idea about the other estimates in the local group. So I mean, as I said before, Milky Way and Andromeda, they have a lot of dwarf galaxies around them. I mean, really close by and also a bit far away. And if you assume what's so-called the Virial Theorem, it's like 2 times the kinetic energy plus the potential energy, the gravitational potential energy is 0. Okay. So if you assume that, you can get the total mass of Milky Way and Andromeda with the dwarf galaxies around it. And this was done in 2014 by Diaz et al. And then the mass is about 2, again, 10 to the power 12 solar masses. Now, there is another possibility how to estimate the mass. This is what's called the Hubble flow. What do I mean by the Hubble flow? So this here, what you see, this is the Hubble diagram. Okay, velocity versus distance. Okay. Now, as you can see, this is the Hubble law here, this line here. But because we are really close to the range where there is also an attraction in between Milky Way and Andromeda, it's kind of like the range in between the expansion, the couple to the expansion, and also the Newtonian attraction. You see that there is kind of like a new line. This is kind of like the new line that estimating the full motion of all of the dwarf galaxies. Okay, so if you really go far away, obviously you get the Hubble law again. But if you're really close by, you get some modification because of the minus gm over r square, the Newtonian attraction inside. So when you integrate the motion of the other dwarf galaxies with this kind of like full, also the attraction and also the expansion, so this is the data that this is the data from the other dwarf galaxies. It is possible also to estimate the mass by the Hubble flow itself, the fit to the Hubble flow. And the fit also gives about 2 10 to the power 12 solar masses. Okay, so what I'm trying just like to give you as a picture, or by the Virial Theorem, or by the Hubble flow fit, it is possible to get a bit lower mass. And also, I mean, it is possible from the timing argument, this is for the first time, it is possible also to get such a low mass if you are including all of the effects that we discussed. Also the correct history, A double dot over A, also the simulation, and also the Large Magellanic Cloud effects. So just like to summarize that, also the important, the effect of the cosmological constant or the Hubble tension in that context, because the value of the Hubble constant is changing also the repulsion force, it's also effectively changing the motions in galaxies nearby. And here what you can see, this is kind of like a local map of the universe. And these are the areas where the Newtonian force is canceled by the cosmological constant. Okay, so I mean, in all of these systems, if you're really close by to the surface, you have to take into account also the lambda effect. So this is just like to give you, I mean, how important also the local effect of lambda is. Okay, so that's all.